링크 공지했나 또?
네, 했습니다.
아니, 두 번째 링크.
저는 바로 문자했습니다.
거기 지금 한 5분에서 10분 단위로 계속 강의가 그렇게 될 거야.
예, 알겠습니다.
그래라. Okay, before we move to the second section, I'd like to explain you my lecture schedule. So we have lectures on Monday, not Monday. Okay, let me check. Tuesday probably. Let me check. Yeah, every Tuesday and then Thursday. So basically, we will have the theory lecture on Tuesday. Okay, theory lecture on Tuesday, and then also the Thursday from 10:30 to like 11:45. So we will cover the theory, and starting from the 11:45. My TA would handle for the example problems. So we have two theory classes on Tuesday and Thursday. And then starting from 11:45, my TA would cover the remaining the lecture. Okay, so let's talk about the tension and compression. So if you click the tab here, you can move to tension and compression very quickly. So here in this lecture note, the learning objectives are here. So we want to understand the flow of analysis first, and then I'd like to emphasize you the three conditions describing a mechanical system. And then also we want to talk about the concept of the normal stress in this section of tension and compression, and then also normal strain. To describe, the characteristics of materials, we want to talk about the concept of elastic modulus, and then the yield stress, so-called yield stress, and the ultimate stress. And then also a similar concept to elastic modulus, and we want to define the concept of shear modulus, G. So we use G to describe the shear modulus. In some of applications, they use mu instead of G. Okay, and we'll talk about the Hooke's law to describe the relation between the stress and strain in these uniaxial problems. And then we'd like to investigate the change in the lateral dimensions, the volume of a bar, to define so-called Poisson's ratio. We'll talk about the bearing stress and the normal and shear stress concepts in the voltage connections. And then we'll define the factor of safety, the concept of factor of safety. The factor of safety is called in 우리말 안전율. Okay, this is a factor of safety. All right, now let's talk about the flow of analysis. Here I devised a diagram to explain the flow of analysis for the structural system for my students. So we have to consider two different scales. The first one is structural scale, and then the second scale is material point scale. The structural scale, so we have two different equations. The first one is a force equilibrium. The force equilibrium means here cat toxin. So in the force equilibrium conditions, here we consider the relation between the different forces, from the external forces and also internal forces. And then the second one is displacement compatibility. Here we define the motion, the deformation of the structural system. And then here we define the motion of the deformation system by using the displacement field. This is the vector, okay? This is the vector. Make sure this is a vector field. And the force is also a vector field. And then using the force equilibrium, so we can extract the information of stress from using the force equilibrium. So once we have the information of stress from this force equilibrium, we toss the information of stress to the material point. Here we use so-called constitutive equations or the material law, okay? Constitutive equation in 우리말 called 구성방정식. And then this constitutive law make a relation between the stress and strain. So although I do not explain you what's stress and what's strain, but at this moment please pay attention to flow of the information, okay? This is more important. We'll discuss the what's stress, how to calculate stress, and what's strain, okay? So what is important is that we have the information of stress and strain only at material point scale, okay? The material point scale. So once using the information of stress, so if you calculate the information of strain, only the strain is tossed to the displacement compatibility to obtain the information of displacement. Okay, look at this. In the force equilibrium side, we have external forces. Using these external forces, and then we extract information of stress. Only the stress is tossed to the material point. Then here we do not consider any forces, okay? We do not consider any forces. In the material point, we accept only the stress to obtain the information of strain. And then here is same. So once we have the information of strain, the strain is tossed to the displacement. Make sure that here in this flow, we do not have any information of stress, okay? So we accept the strain to get the information of displacement. Also, you can take opposite flow of analysis. We start from the displacement first, and once we have displacement field to describe the deformation, then we calculate the strain. Then we toss only the information of strain to the material point. Then, so we calculate the corresponding stress. The corresponding stress is tossed to the force equilibrium side to calculate all the reactions and check the force equilibrium condition. Okay? And to complement the flow of analysis, for example, here we can set displacement boundary conditions such that how my structures are supported. And then also we can prescribe the information of external forces. These are boundary conditions, okay? We have boundary condition, BC. So on the right hand side, we have displacement boundary conditions. And on the left hand side, we have force boundary conditions. Do you have any questions for this diagram? This diagram is very useful. And then this diagram is summarizes the flow of analysis in a very simple way. Okay, here we have force equilibrium. So let me talk about force equilibrium condition further. So force equilibrium, to check the force equilibrium, we use Newton's second law. So if you already studied the elementary physics, then you are already very familiar with this Newton's second law. So Newton's second law is this. Let's say, imagine we have a body. So if you consider sum of all the force components acting on the body, that should be equal to mass times the mass of the body and then the acceleration of the body. This is Newton's second law. To understand Newton's second law, we have to start from the definition of the force. Okay, let's imagine that we have a body, okay, whose mass is given by m here. The initial velocity is v naught. And then if you consider this first, to calculate further, we have to introduce a coordinate system, isn't it? Before any analysis and before any mathematical calculation. So we need define a coordinate system first. Otherwise, we cannot do any calculation, isn't it? So let's introduce this Cartesian coordinate system. So once we have this Cartesian coordinate system, so I can decompose this momentum. The mass times velocity is the momentum. Is given by p, the momentum. This is also vector, okay, vector, because the velocity is a vector. And then this velocity can be decomposed into two different components following the direction of these orthogonal coordinate systems in x direction and y direction, isn't it? The v naught x is the velocity projection to the x direction. So make sure here EX represent unit normal in the x direction. The EY is also unit normal in the y direction. So if you are familiar with the trigonometric functions, we can easily calculate the projection in x direction using the initial the magnitude of the vector v naught. The v naught times cosine theta naught is the projection of this velocity to the x direction. Okay. Also, the y direction projection can be easily calculated in this way using the sine function. Alright, so let's imagine that this moving body is contact with a rigid wall here, and certainly it is pretty sure that because of the interaction between this rigid wall and the moving body, and then this body changes its direction, isn't it right? Initially its motion was prescribed by v naught in theta naught direction, but after the introduction, the body suddenly changed its direction of motion in this way. Now also the velocity changes to v1, and the direction is changed to theta 1. Okay, so there was change in the momentum. The change of momentum can be calculated by the vector mechanics p1. The momentum here is given by p1, and then minus initial momentum p naught. Then if you use the vector mechanics using this coordinate system, so we can calculate the change of momentum very easily. Okay, so the change of momentum. So according to Newton's definition, the force is defined this way. The force vector, the underbar means a vector, is given by the limit. The time is approaching to the infinitely small time, and then this is defined by delta p and then delta t. Okay, this is the definition of force. So according to Newton's second law, if you have any force, okay, if you have any change in momentum, the change of momentum is equal to the mass times the acceleration. So let's imagine that we have a stationary system. Stationary system means the acceleration should be equal to 0. Okay, so for our structural analysis, we use these conditions to satisfy the sum of all the force vectors acting on this structural body. This is a vector for all the forces should be equal to 0, which means we check the force component in the x direction. What I mean, because we already have this coordinate system, so we have to check each component individually. Okay, the x component and the y component. Okay, these two should be equal to 0 in these two-dimensional problems. So if you want to consider three-dimensional problems, also we have to consider the z component too, isn't it right? Okay, so let me talk about the coordinate system further. So here, so typically we use x coordinate and the y in the x direction, y direction, and z direction. Okay, and then depending on authors in like advanced the research papers, instead of using x, y, z coordinate system, so we name just x1 and x2, x3. Okay, so these are the same. And then let's talk about the normal vector here. in your textbook, the elemental physics textbook, typically they use, you know, nx, isn't it right? Nx. Also in this direction, ny, okay? And also in this direction, nz. But according to these initial notations, instead of using this n1, the n2, n3 is the same. So as I note here, also we may want to use ex, ey, okay, the ez. So all are same notation, okay. And also instead of using x, e1, the e2, and the e3, okay. Please do not confuse with different notations. Do you have any questions? Any questions? Alright, so now let's talk about Newton's apple here. So this is a really famous apple, isn't it right? Very famous apple. So let's imagine we have an apple tree and then an apple is falling to ground. So free falling, okay, free falling. And then because of the gravity, this apple is subjected to, you know, non-zero force here, non-zero force. So the force is equal to the gravity mass times of this. And then Newton's, if you look at here, Newton's second law, this is equal to mass times acceleration. So which means the acceleration of the apple is characterized by the gravity acceleration, isn't it? Gravity acceleration. And then if you look at the apple here, let's imagine a small piece of apple here. Okay, look. So all the points in this apple subject to the same gravity, isn't it, right? The same gravity. So this kind of force is called body force, because the force is acting to, you know, every point, every piece of my domain. Okay, here domain means in 우리말 영역. Here the domain is my domain of consideration is my apple here. Okay, apple. So here I'd like to define different kinds of external forces. So make sure that the gravity has nothing to do with this apple, isn't it, right? The gravity is caused by some external action. Let's draw an actual apple here. Okay, apple here. And then as I told you, any point, okay, any point is subjected to same gravity loading. Oh, sorry. Same gravity loading. So this kinds of load is called body force, okay? Body force. So body force is called 최적력. Okay? So typically this body force is caused by the gravity and then also the magnetic force too. Okay? They are typical examples of body force. And then if you grab this apple with your hand, then we can apply the external force from outside, isn't it right? So this is called traction. In 우리말 표면력. Okay, traction. And then here, because if you use hand here, my force is acting on, you know, contact area of my finger between, you know, contact area between my finger and apple. Okay, that's why usually the traction is distributed. The force is acting over a certain area of my body. That's why we call it. Typically, traction is 표면력, is distributed. But if distributed area is too small, okay, the force magnitude is concentrated to very small area, probably we'd like to approximate that force distribution using concentrated forces, isn't it right? That force It's approximation of this force using a vector. This is called, let me check my window. Correct. Yeah. This is called 집중하중. 집중하중. This is called 분포하중. Okay. In English, traction, or if you translate 분포하중 directly, distributed load. The concentrated load is approximation of a certain distributed load over very small area. Okay, this is called concentrated load. Do you have any questions up to this point? No questions. Probably here you are interested in the sign of force component. So make sure that this is really important. The sign of force component must be determined by the choice of your coordinate system. Let's go back to Newton's apple here. Okay, so I have force in the downward direction, because I have, my y default coordinate, the direction of my default y coordinate direction, and upward. So which means the sign of my gravity acceleration, or I mean the mass times the gravity. So here I do not have bar, which means scalar quantity. Because of the coordinate choice of coordinate system, this is minus. Okay. So again, here the bold face means the vector. Okay. But I mean G bar is a vector, and as in my lecture note, the bold face is also the vector, same thing. Okay. If you measure only the magnitude, if you consider projection, that depends on the choice of the coordinate system. So with this choice, minus. But how about, let's say, if you choose a coordinate system like this, for example, this x and y. So if you choose this coordinate system, surprisingly, its sign is changed to positive. Okay, so everything depends on the choice of coordinate system. Don't be confused with the sign convention of the force components. Make sure the forces are vectors. But force components are scalars. The sign of force component should be determined by the choice of coordinate system. Okay, next subject is free body diagram. Let's imagine the same mass here, but we have a hanger here. And then, as we discussed already here, this mass is subjected to gravity loading, the mass times the gravity acceleration. But because of this hanger, is in equilibrium, isn't it, right? It's in equilibrium. So if we have a structure system in equilibrium, then which means even if you consider small part of the structure system, that small part should be also in equilibrium. So let's consider the small piece here. Okay, I want to consider this part. Okay, this part. Now we already understand that we have one external force, the mass times gravity. This is the external force caused by the gravity action. And that because we cut here, we have imaginary cross section, isn't it, right? Imaginary cross section. So we don't know what's here. But according to the force equilibrium, this is my static system, isn't it, right? Because we consider the small part of my structure system from the original structure system. If you consider all the force components acting on this small piece, ABC here, then sum of all the forces, okay, should be equal to 0 because it's in equilibrium. Okay, let's consider only the force components. This is my coordinate system, isn't it, right? This is my coordinate system. If you consider instead of vector, if you consider only the force component, okay, what is the sign here? The mass times the minus of mass times and the gravity acceleration should be equal to 0. It doesn't make sense, isn't it, right? This is non-zero quantity, so it cannot be equal to 0. So which means I have something more here. Okay, something more. Okay, something more. So this something more, according to force equilibrium, this should be equal to mass times the gravity acceleration. This is called internal force. In 우리말 내력. Okay, 내력. So we need that thing, okay, to satisfy the force equilibrium condition. Otherwise, the force equilibrium condition is violated. Okay. So using this free body diagram, we can understand that there must be a certain internal force to satisfy the force equilibrium condition. The free body diagram in 우리말 free body diagram is called 자유물체도. Okay, so once we calculate internal force at on a cross section, so we can consider further smaller one. Let's consider only the AB segment. So we already know that here we must have mg here. Okay, mg here. But to satisfy the force equilibrium, we can easily understand that on B side, we must have exactly same quantity, but in opposite direction. Okay, that's how we can calculate the internal forces by using force equilibrium condition. So here the free body diagram include all the applied forces and moment, the reaction forces and moment, and the connection forces between the individual components. This is very useful to identify the internal forces in the structural points. Very useful. Do you have any questions up to here? Okay, let's consider another example for free body diagram. So we have a vehicle on top of this my structure here. And then the vehicle load should be supported by these two reactions, isn't it, right? These two reactions. Probably we can calculate, the magnitude of these reactions using the force equilibrium and the other mechanical laws. Okay? So this is the entire domain omega. So if you consider small part of the domain, let's say omega 1, okay, omega 1, then I have an external force F here, and then I have a reaction force here. So if you consider only these two forces, so of course it is obvious that the force equilibrium cannot be satisfied. But because we choose a part of structure from the entire domain, which is subjected to force equilibrium, so we understand that there must be some additional actions at this cross section, isn't it, right? So using the force equilibrium, we can calculate the internal forces. Okay, this is a role of free body diagram, where to use free body diagram. Okay, so now the next subject is a reaction force. Reaction force in 우리말 반력. Reaction forces in 우리말 called 반력. Okay, 반력. The reaction forces, forces as structural support. For example, these are structural support here. For example, this is hinge and this is a roller support. So we'll discuss, the characteristics of different support conditions later. But anyway, all the structures must have, the support conditions. Okay, let's consider a cantilever here. The one side is fixed. This is a fixed support. And how do you call this? This is the free end. Okay, 자유단. 자유단. This is 고정단. Okay, 고정단. And the forces at structural support, which result from the action of applied forces to the structure, are called reaction forces. Because we have these external forces are obvious, because this is a condition of the problem, isn't it, right? But the magnitude of reaction is not given, so we have to calculate the reaction to satisfy the force equilibrium condition. So any forces are not given explicitly, but we have to calculate by using some rules of structural engineering systems. These are called reaction forces. Okay, and then depending on the degree of freedom under consideration, those can be the force and moment. For example, let's consider this cantilever. We have force here, isn't it? To satisfy the force equilibrium in the vertical direction, we need to have one reaction in the vertical direction, isn't it? And then also to satisfy the moment equilibrium, otherwise the structure would rotate. We need to provide another reaction force here. That's why here on this fixed end we have 2 degrees of freedom. First one is for the translation, and the second one is for the rotation. Even if we consider a single point, we need to consider 2 degrees of freedom to discuss the reaction to satisfy the force equilibrium. The internal forces, I already explained you the concept of internal forces. Okay, the internal forces are not given explicitly either, but if you consider free body diagram, then we can easily calculate the internal forces. Okay, so look at the flow of analysis. So here we must have the external forces. Using this information of external forces, we can calculate the information of reactions and internal forces. Okay, so we are talking about this force equilibrium side here. Okay, so now let's talk about the equilibrium equation. As I told you, in the vector form, the sum of all the forces should be equal to 0 in a stationary system. The stationary system doesn't mean that a static system, okay? The stationary means if a body is moving with the same velocity, okay? Same constant velocity. This is also called a stationary system, okay? Stationary system. If you want to consider static system, so we need to provide a support condition not to move the structural systems. The equilibrium condition for the stationary system, sum of all the external forces should be equal to 0. This is the definition of equilibrium condition. And then also in the general concept of external forces, also we can consider moment too. Okay, moment too. Sum of all the moment acting on my structural body should be equal to 0. This is the vector form of force equilibrium condition. Okay, this is a vector form. Well, of course, using the vector form, it is not convenient to carry out the calculation. It's better to use the scalar form using the coordinate system. Okay, at first we have to define a coordinate system. For example, the x and y and z coordinate system. Then we check the force equilibrium for individual force component. Okay, sum of forces in the x direction should be equal to 0. Sum of force components in the y direction should be equal to 0. Z direction is also equal to 0. As I told you, instead of x, y, and z, we may want to use 1, 2, 3 instead of x, y, z. This is more general, and then this is more convenient to handle so all kind of formula. So I prefer to use the initial rotation. But in your textbook, they use x and y and z. That's why I keep these notations. Sometimes I use 1, 2, 3 initial rotations. Please keep in mind that they are the same. Okay. Alright, so now let's talk about normal stress. Alright, imagine I have a bar here. This bar is subjected to a pair of forces, force P here. And then if you cut here, by the way, let's imagine I have a bar. So these two forces are vectors, isn't it, right? Okay, let's consider force equilibrium. As I told you, before any analysis, we need to introduce a coordinate system. Okay, sum of all the forces in x direction. Okay, x direction should be equal to 0. Okay, let's consider the force in the right hand side. This is what? The P. Because of this coordinate system, this is positive P, isn't it, right? And how about this? This is negative P. So which means if you consider the force equilibrium, the minus P plus P is obviously, this is trivial calculation, it is equal to 0. The force equilibrium is beautifully satisfied, isn't it? So now I want to cut here. I want to consider this free body diagram for this segment. Okay, since I have external force, we already know that, but probably here we have certain action. For example, because we don't know the direction yet, so let's consider it's acting in this direction. Let's say N. Okay, so now we have, then what's the sign convention for this N? Because this is my coordinate system. For the component form, this is minus P, and this is also minus N, isn't it, right? Minus N. So let's use the force equilibrium. Sum of all the force component in x direction should be equal to 0. This is minus P, and then minus N. Then we can easily conclude that the N is equal to minus P. What does it mean? That this means the direction of N is in the left hand, left direction. It should be in the right hand direction. It should go in this direction, isn't it, right? Then if you correct this, the N is equal to P. Okay? So make sure that, but this point, on this cross section, we have infinitely many points. These infinitely many points are connected, connected each other without having any gap between these two, the free body. So that's why we can define some distributed action over this cross section. So let's divide the internal force. Let's divide the internal force, the magnitude of internal force, by this area. This internal force divided by the area is called normal stress, sigma. This is called 내력, internal force, and this is area. This is called 수직 응력, normal stress. Okay, so we have the definition of stress. Because to define the stress, we divide the normal internal force by this area. The unit of the stress is force per unit area. So we have we can define several different kinds of the stress unit. The first one is the PSI, as given in the textbook, pounds per square inches. Okay, this is PSI. And the KSI is kips. Kips is kilopounds. Okay, kilopounds per square inches, KSI unit. And then here the Pascal. Pascal is newtons. Newton is the unit of force, isn't it, right? The Newton per square meters. This is Pascal unit. So if you consider 1 Pascal, the 1 Newton per square meters, then the stress is very small one. For structural application, instead of Pascal, in many cases we use kilopascal. For the geotechnical application, the kilopascal means K stands for 1,000, okay, 1,000 Pascal. And then for the structural engineering application, we use megapascal. This is 1,000 times Pascal. The megapascal is, mega means million, isn't it, right? 10 to the power of 6 Pascal. And to define the elastic modulus of concrete and steel, we use the gigapascal. Gig means 10 to the power of 9 Pascal, okay? This is the unit of stress. And then let's define the normal strain. The normal strain now, okay, look at this. To define the stress, so we are here, okay? We only consider force equilibrium. So now let's define the strain. To define strain, so forget about the force stuff. So let's only focus on deformation, okay? What causes the deformation? Forget about it, okay? What is important to define a strain is just deformation itself, okay? We want to consider only the deformation and only the motion. So I want to consider only this condition. Make sure that these three conditions are independent of each other, okay? Independent of each other. They do not, you know, we consider the flow of information from, you know, the displacement comparability to the constitutive equation to the force equilibrium, okay? Or the force equilibrium, the material law, and displacement comparability. But these three conditions are independent. So now let's imagine the deformation. So although I have this arrow, let's forget about these arrows, okay? So we have initial body, but this body is stretched by some reason, okay? It can be, it can be, you know, it was caused by, it might be caused by the forces, it might be caused by the temperature increase. Anyway, let's say we have length change. Initially the length was measured by capital L, and after the deformation it was measured by L plus delta. And then the deformation, the density of deformation over the distance can be measured by, you know, the elongation delta divided by the original length. This is called strain, okay, strain. This is called strain. Because to define a strain, we divide the elongation by the initial length. This is the dimensionless quantity, isn't it? This is a dimensionless quantity. To use the definition of strain, we have certain requirements. The first one is the bar is prismatic. What I mean, there is no change in the cross section. So we must have the same cross section from the starting point of my member and to the end point of my member. And then another one is the material should be homogeneous. What I mean, we want to use the same material for the overall body of this member. Then we can use this definition of strain. So let's talk about the examples here. Okay. All right. Say, let's simplify the problem using two-dimensional configuration. So I have a cylinder. And then it is subjected to 26 kilopounds. Okay. Let's try to calculate the stress here. By the way, I didn't mention the sign convention of stress. Here the sign convention of stress is what? If the material is stretched, then we are going to call this as the positive stress, okay? If material is compressed, then my stress is negative. This is sign convention of my stress. So we'll revisit the definition of sign convention later. The strain, same. If material is elongated, then strain is positive. The material is compressed, the shortened, then my strain is negative. Okay, here let's try to calculate the stress quantity. Alright, so this is called external force. This is external force, isn't it, right? what is the very first step that before any analysis? Before any analysis, the very first step is to introduce a coordinate system. Let's define my coordinate system. Okay, and then we need to calculate the reaction, isn't it right? So I must have certain reaction. Okay, so let's try to use the force equilibrium. Sum of all the forces in this direction. It follows from this coordinate system. All the force component should be equal to 0. This is the definition of equilibrium system. Then R minus, look at this direction is downward, but the positive direction according to the definition of my coordinate system, the upward is positive. That's why minus 26 kilopounds should be equal to 0. That's why we can determine the magnitude of reaction very easily. The reaction is equal to 26 kilopounds, isn't it? So now let's try to calculate the stress. The magnitude of stress is what? The stress by the definition is what? The internal force. If you cut here, I have internal force. Using the free body diagram, my internal force is equal to 10 is magnitude of 26 kilopounds. The internal force divided by area is equal to 26 kilopounds divided by the area. What's the sign? Because the material is compressed. That's why the sign is minus. Okay. All right. Here, I'd like to take a break here. In the next Tuesday, we're gonna talk about the material law. Okay. But because today we just started this lecture today. Today we do not have TA class. Okay, see you next Tuesday. Do you have any questions before we finish today's lecture? So as I told you, I'd like to take a break here after each section here, so that you can find my video lecture very easily. Any questions? No question, huh? Okay, thank you. Let me finish my lecture here.